Oh, my bad. I think I use M samples, right? And the second one, the typo, it should be RM. Okay. All right. So this is good. So basically, I want to minimize this, and so we use the inner product. So recall. So we've defined two types of inner product. The first is a vanilla L2 inner product. It's just X inner product with itself, and this is X transpose X. Okay. The second one is Q inner product. It's QX times X, and this is X transpose QX, and this is for Q being symmetric, positive, symmetric, positive, definite. Sorry. So positive definite is a single word. Then we just plug in. So this is pretty much like a quadratic function. So for example, if we want to do it step by step, this is AX times X minus B, subtract B, inner product with X minus B. And this is AX inner product with AX, subtract AX inner product with B, subtract B inner product with AX plus B inner product with B. So we're minimizing. Okay, so we're minimizing this. And we couldn't help but notice these two are the same thing. Okay, because of the commutativity of the inner product. The first guy inner product with the second one, the same as the second one inner product with the first one. So this one is, okay, we minimize X in Rn. This is AX inner product with AX minus 2 times AX inner product with B plus B inner product with itself. Okay. I mean, the quadratic function we learned is 1/2 X transpose Q B transpose X. Okay, we minimize. We learn how to minimize this function for QSPD, and it's okay to add a C here. Okay, to add a constant, because the constant doesn't change the location of the local minimizer. It's just change the value of the minimum value. So now we rewrite this as in the form. So this equals as minimum. So the first one is AX transpose times AX minus 2 times AX transpose. Yeah, let's use this form. That is B times AX. So we have B transpose X. Okay, so B transpose AX, and then we'll have B transpose AX. And then plus like a constant C. Okay. So where this C is defined by this B norm square. B is like a given vector, so it's and this is the same as, okay, this is the same X transpose AX, subtract 2 times B transpose AX plus C. Okay. All right. I mean, so now this is our matrix. Okay, it's just, this matrix is only non-negative, it's not positive definite anymore, but we can still take derivative. So if we take derivative in the gradient, okay, all right, so we take derivative of this, we get Q minus B, right? So we do the same thing for this. I mean, so if we take derivative, we get 2 A transpose A, okay, subtract 2. So originally it is B transpose. So we get QX minus B, so gradient, let's say this is our G, so gradient G is this guy. Then for this is we have to take transpose. So this is B, but this is B transpose. So here, B is B transpose, we'll take transpose, so we have this. So now this is, sorry, we have an X here, my bad. Okay. Now this is our gradient. So this is we hope our local minimizer will make this 0. So in linear regression, so for example, if we have learned a statistical linear model class, we learn when we perform, before we perform linear regression, we want to remove repeated entry or repeated data entry. And we want to remove highly correlated features. Why we want to do that? Is to make this guy as invertible as it can get, because if we solve this, so this is nothing to do with the homework. I just want to say a few things why we're doing that. So we set this to be 0. It's equivalent to solve, right? To solve this, if this is invertible, if we have removed all the repeated samples and removed linearly dependent features, then this can be solved. So this is called normal equation of a linear model. Okay. So also in the homework, so now let's take the Hessian. The Hessian is just this guy. So 2 times transpose A. Okay.
I have a question. So when we did the first derivative of the B transpose X, we took the transpose just like you did over there. So are we doing the same thing when we do the second derivative as well?
Yeah, we did. This guy's transpose is itself.
Okay.
So, so we can use homework 1. So in homework 1, we have derived the following thing. That is the gradient. So if G is, so in homework 1, we had X transpose AX. A is not necessarily symmetric matrix. So when we have this, the gradient G is A plus A transpose X. And Hessian of G is A plus A transpose. So And so for the second one, for the second one, it's just A is a diagonal matrix, okay? What I want to mention is this is slightly different. Think about this, okay? So in the regular minimization problem, okay, in a regular minimization problem, our convergence depends on, so this is our rate of convergence we proved for gradient descent, and if we choose the best learning rate or step size, and where kappa is lambda max of q divided by lambda min of q. Okay. All right. So things is slightly different here. Okay. Because q is now 2 times A transpose A. So 2 times A transpose of A is, if we use the expression, we'll get this is basically 2 lambda 1 squared, 2 lambda 2 squared. Okay. All right. So the condition number of this matrix, so we're looking for condition number of this matrix, because this matrix is our Q, or a multiple of Q, okay? So our condition number becomes, which one is bigger? Lambda 2 is bigger, so it's 2 times lambda 2 divided by 2 times lambda 1. Then we have to square, so it's squared, okay? All right?
Why is it squared? Oh,
yeah,
it's squared there. Okay.
Condition number is defined by the.
Okay.
So this is like let me write down. So this is the condition number of A transpose A, and this actually equals kappa A squared. Okay. This explains. So this explains what? This explains linear regression. Is yield conditioned. Why is yield conditioned? Think about this. If we have condition number 100, a square of it is 10,000. Okay? So if it's positive definite, okay? So the original quadratic function converges in 100 steps or something, Then if we plug in this to the linear regression, the best case scenario for arbitrary initial guess is it converges in 10,000 iterations. Okay? So linear regression is called an yield condition problem. So that's why, even before we do this data manipulation, so suppose this A is already a good matrix. We removed all the linearly dependent features and all the repeated samples, it's still a yield, condition problem. So, but yeah, that's a motivation of this problem. So you guys may see in future in your research, So don't be surprised that linear regression converges very slow. Versus if we have a good conditioned system. So we will talk about it next time. But so now let's now present. Okay. Conjugate gradient. Opposite. So I forgot which venue, but there was some ranking of the top 10 algorithms of 20th century. So conjugate gradient is one of them. And, so the others like SVD and things. So the name is Krylov subspace method. So it's named because the convergence, to prove the convergence, we need to rely on this. But so Krylov subspace method is top 10 algorithm back in the 20th century. So, but let's recall the setting. I mean, the setting is a long setting. So we have a function, okay, and it's a quadratic one. So in general, this can be very relaxed. For example, Q here is SPD, right? It's a quadratic function, but in general, it may not be a nice quadratic function form. It may be a even more complex, but as long as the Hessian, which is Q, is locally positive definite, then we're in good shape. But this algorithm can be generalized in many different respects. Okay. But we'll talk about this much later. So, and our goal is to minimize this. Okay, so our goal is to minimize. All right. So it has, so this problem, when Q is SPD, symmetric positive definite, it has a unique local minimizer that is Q inverse times B. So, but the story is computing Q inverse is expensive. Okay. So what we want to do is we use gradient descent algorithm to find a point that has 0 gradient. Okay. So this is like the story, the first part of the story. And then we use the property of inner product. We derived that the current function value subtracted the function value at the local minimizer is 1/2 x subtract x star, which is our local minimizer in the Q norm squared. Okay, so now we've converted a minimization problem. So we minimize the function. It becomes we minimize the distance of the current x we're at with this local minimizer. So it becomes we want to minimize the distance. And now then the minimization of this. Okay. So to minimize the minimization problem of this. So is equivalent to find the projection. Okay. So, all right. Okay. To find the projection in a subspace. Okay. The steep is the descent, the subspace is the line. All right. So in a subspace, of Rm. Okay. So steep is the descent. This subspace S is a line. It's a line in that it's a span of the gradient at the current iteration. So there is a single search direction. Okay. So CG is at every iteration, okay, is we have a dimension k+1 subspace, okay? So if we denote this as G at the kth iteration, then the CG is we build an increasingly like a dimensional, okay, so an increasing dimension subspace that its dimension increases by 1 at each iteration. All right. So, and not only we want to do this, we want to orthogonalize it. So we want to orthogonalize this on the inner product of Q. Okay. So what does it mean by orthogonal? Is xy is orthogonal, x and y are orthogonal is equivalent of x inner product with y, or x transpose of y is 0. And if x is Q orthogonal with y, this is equivalent of asking x, y, Q inner product of x transpose qy, and this is also y transpose qx, which is 0. Okay. And this Q has to be SPD. Right. So this is the story. And now, because of this Q orthogonality, once we search the projection, okay, so given x0, which is our initial guess, this is our initial guess, like it has nothing to do with our algorithm, we can choose randomly, you know, so what happens is, at the k plus 1th iteration, we find the projection into the subspace S, which is Sk, in a Q projection, and so if we do this, it's equivalent of find the minimum of xk plus 1 subtract. Well, it's belong to x initial guess, then plus our vector in this search subspace. We minimize this norm, that is. So we minimize the distance of this guy to the local minimizer under the Q norm. But we don't know this yet. So we have to build an algorithm that is equivalent to this minimization problem that is efficient. Okay, so here comes our conjugate gradient algorithm. So this is the full story of why we want to introduce, or why, theoretically, how this method is invented. So here is our conjugate gradient algorithm, so CG method. Okay, so I forgot to mention one last step. And because of the Q orthogonality, the gradient at the k plus 1th iteration, which we take gradient of this one. Okay? This is defined as the gradient at k plus 1th iteration. We proved last time. Okay? Number one, this is orthogonal to all the bases here. So this is Q orthogonal. So this is dI is orthogonal to dj in Q norm. Okay. If we have this, then we have two. That is, this guy is orthogonal in the regular L2 norm. For I is 0, 1, 2, dot, 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 up till k. And the gradient at k plus 1th iteration is orthogonal to dI in the Q inner product for I from 1, 0, 1, 2 up till k minus 1. Okay. So because of these two orthogonality, we can build an efficient algorithm for CG. Okay. So what happens is we can have a three-term recursive formula, that is, so for k is 0, 1, 2, etc. So what happens is our k plus 1th iteration is, so and we define so this given x0 and define g of 0 equals the first d of 0. So the first basis vector is orthogonal. We just choose as the gradient, as a negative gradient, which equals negative gradient at the initial guess. Okay. And each time we add the negative gradient direction to the subspace, and then we orthogonalize it. Okay. So now what we have is, so we have this recursive formula. Okay. So where alpha k is negative 0 against dk and dk q. And then, say it again.
Okay.
Yeah. Okay. And then we compute the gradient. Okay. So we update the gradient. So first is, this is like descent. Okay. Let's say find the minimizer with descent in sk. So this is like step 1. And step 2 is find gradient. Find the negative gradient. So the second step is we only have to correct. So we compute the gradient, but we only have to correct the gradient. So this is a gradient at next iteration. We only have to correct the gradient using previous gradient, and then we add this direction k, which we obtained. Okay? So next step is make it Q orthogonal. Q orthogonal. And that is dk plus 1 is minus g at k plus 1 iteration plus beta sub k dk, where beta sub k is computed by dk q norm, and this is gk plus 1 dk q norm. So this is a full conjugate gradient, 3-term conjugate gradient algorithm. Okay. So next time we'll analyze this. So the first step is computing the projection of xk plus 1 in this subspace. Okay. Second one is we find the gradient at the k plus 1 iteration, and then we add the gradient to the subspace, and we make it Q orthogonal. So the amazing thing about this algorithm is we don't have to store all the variables. Okay. Neither do we have to evaluate this function, its value at a specific point. Okay. To think about how good this is sometimes it's easier to measure gradient than the function itself, because we can send like a perturbation to the system. We measure its response, we get a gradient. Okay? We get how it's changed with respect to a certain perturbation. And so the main thing that this is no need to store. Okay. If we look at the formula, there is no need to store all the directions. If we look at this formula, we only need to store this. Only this is needed, okay? Only dk is needed to get xk plus 1. All right. Think about it. We have a subspace of dimension k plus 1, but this is the only vector that is needed to minimize in such a big subspace. Yeah. So, okay. But we will show that the convergence next time. So, but now let's so it still has a linear convergence. Okay. So it still has a linear convergence. So the convergence of this is the convergence. It has very similar to gradient descent algorithm. In fact, it's even written, in the same format. Okay. So we multiply. This time we have a constant. So this is square root of kappa subtract 1. Square root of kappa, which is kappa is condition number, it's plus 1. All right. Originally, if our gradient descent algorithm converges in 100 steps, then CG will converge in 10. Okay. And we can show that even if sometimes we hit very close to the eigen direction of this matrix Q, which means at one step, we happen to be, in the eigenvectors direction, or very close, then the CG will normally converges in less than maybe 2 steps. Okay? Yeah, but that one will be in our next homework about CG. Okay, so now let's So I uploaded a lecture on campus. I'm just curious, what is the quickest way of getting to campus from this default? Oh, okay. Thanks. There we go. So our coding homework 2 will be available later today. So it will be in a similar format to the first one. So again, let's open up. There we go.
Friday. Later.
All right, so let's open up our notebook. Better?
Yeah.
Okay. All right, so so this is so I want to like say our goal. So our goal is write our own optimizer, and we'll be familiar with PyTorch code tradition, which is a vectorized this coding tradition of numerical linear algebra. Okay. So more advanced is so the best. I mean, code editor I recommend is Visual Studio Code. So I've been using PyCharm for perhaps 10 years, but I switched to VS Code about 3 years ago and never went back. Okay. So and even if you are like an Emacs user, or BIM user, you can simulate the experience of Emacs and Vim in VS Code. So today we'll learn some advanced manipulation of matrix vector multiplication. Then we'll build a simple iteration gradient descent algorithm. And the next coding lecture we'll learn the powerful autograd from PyTorch. Okay. So this is the reference. So if you're interested in how to implement a neural network from scratch, you can visit this. So I think I implemented a long time ago and for pedagogical purposes. So let's import NumPy and Torch. Okay. So NumPy is normally okay. So let's review how to build a tensor. So we can do for example, Torch. We can do this Torch tensor, and we can do I don't know 0.5, 0.7. So and now let's print it. So for example, so now we get this Torch. So if we just want to show its value, I think we can do this. Oh yeah, okay. So scalar. For example, if we want to print a value. And the other way to build a tensor is, for example, we have some built-in command, such as arrange. So if we do arrange like 8, so we'll get a tensor of length 8 that starts from 0 and up until 7. So we have other initialization, such as 1 I, for example. So this is pretty much the same thing as MATLAB I command. For example, this is identity matrix. And we can have, for example, we can have a random number. And then in this parentheses, we can give Torch the size, the dimension of the random number we want. If we want to build a 3x2, matrix, random number, we can do this. So this is a 3-row, 2 columns. So a very nice thing about Python is it has a polymorphism. What does it mean is, so if we want to apply a function, okay, to this variable, so for example, we can, so for example, if we want to sum up a variable, if we do this, I'm not sure if NumPy is already back compatible with X, but maybe this is a bad example, but let's do sum. Okay, so if we do sum, okay, we'll get 4, right? So this is right. Okay. However, if we sum, for example, this guy, let's see what happens. I do believe Python will throw an error that this has to be, I'm not sure if PyTorch is made to be compatible with standard Python. Oh, it does. Okay, good. So, how about NP? Okay, this now gives us error. This is type error. Okay, so Python is not, PyTorch is made compatible with standard Python sum, but not NumPy sum. Okay, so why? Because NumPy sum has to accept only a variable as a NumPy tensor. However, the good thing about this is Python, this polymorphism is agnostic of this type. For example, if we do Torch a range 8, okay, so we can just use its method .sum, okay. So give us this, and so it doesn't matter. Think about this. So if y is non-pi, same function, print y sum. So it's kind of, its mechanics are the same. So in this way of applying a function is, we don't have to know what variable of this is. As long as this method is defined, this is good. Okay, so this is called a polymorphism in any object-oriented language. So now let's do matrix multiplication. So last time we had torch mm or math mol. So this is torch. So this is a function for matrix multiplication. Okay. So if we do this, we pull up the help. So math mol. Okay. Matrix multiplication of two tensors. Right. So for example, what we can do is we can initialize two tensors. For example, A is random. For example, we have 100 rows, 20 columns, and X is a vector of size 10, okay? And we want to, for example, we can print. Yeah, let's don't print. 20, sorry. So let's do 2, okay? So let's print, okay? So A, torch math mol, A, X. Okay. So we get a dimension 2 tensor, all right? So what I want to mention is this dimension match, okay? So if we have dimension 2 and 20, this 20 when we do matrix multiplication, so the first dimension of this must match the last dimension. And the other way to do matrix multiplication is using this. Okay? So dot needs that. Okay, so yeah, I guess this is where we want to introduce some manipulating the axis. So it gives us error. 1D tensor expected, but got 2D and 1D tensors. So sorry, this is MM. So map 2 must be a matrix. Okay. So this is A map 2. So which give us the next topic, which is manipulating the axis. Okay, so this gives us a runtime error, which is this guy. So it says map 2 must be a matrix. It means this is not a matrix. How do we make it a matrix? Okay. So let's see this example. I want to do this. Let's do this first. So this is a vector. Make it capital. So this is a vector if we print T, all right? So it gives us this vector. And how do we make it a matrix? Is we can use the following thing. That is, if we want to expand. So if we want to, for example, this is a, so if we print T's shape, this will give us like 3, okay? So it's like a size 3 vector. Now, how we can expand its dimension is we first use column. This means, it's a current dimension, and then we add a num in the second one. So if we print this guy's shape, we'll find it becomes a matrix. Okay? So it becomes becomes a matrix of 3 columns and 1, 3 rows and 1 column. So now let's try this again. So this gives us error, right? So this gives us error. Mat2 must be a matrix. So then what we do is we simply do, okay, now we're good. So I mean, it's how to like play with the dimensions. So the other way is we use squiz. Okay, so for example, so what we can do is we do onsquiz. So there is a command onsquiz, and its input is dim. Okay, so if we onsquiz at dim 0, we'll get a 1, 3 vector. Oh wait. Oh yeah. So x. Let's print x. Okay. Let's print x first. So x has print x, and let's print x's shape. So x is now like a 20 size 20 vector. Okay. So if we do, so we can tell the difference. So this is a tensor with a single bracket, all right? But this is a tensor with, there are 2 brackets. They're different. We can actually print its shape. We'll see its first dimension got a onsquiz. Okay. If we print this, we got the first dimension, which is dimension 0, okay? So we have an extra 1 here. And the other common way is, so there are 2 nice things about Python is we can, 0 is always the first element dimension, whatever, and -1 is always the last. We can unsqueeze its last dimension, and we'll get 20 and 1. Okay. All right. So, so this is one way to manipulate the dimensions. So if we get a dimension error, most likely, if we get dimension match for matrix and vectors, most likely it's about so there are some dimension mismatch. And next we talk about reproducibility. So for example, we can fix the seed. Okay. So if we fix the seed, what happens is this guy won't change. But it's indeed empirical distribution is a random, is a normally distributed random number. Okay. But it gives us a fixed number each time. Okay. So let's run this cell. And so today we'll try to implement a single layer neural network, the simplest one. But a single layer neural network is just a matrix vector multiplication. Okay? And then we'll apply a function on it. So, and now for example, now we create a random number that has n rows and b sub n dimension. N is 1, so we have 1 rows. And yeah, let's skip. But yeah, let's still do this. So this is a random number of 5 rows and 7 columns. So, and also the nicest thing about this Python indexing is, unlike MATLAB, we have to specify the index of, even if we use column, we have to specify every dimension. But in Python, it's different, okay? So if we put this, if we put x0 as its index, by default, it returns the first dimensions like row 0. So if we do, yeah, let's do 3, okay? Which is the 4th row. Row 0 is the first row, so we can do x3, okay? So it returns the 4th row, which is this guy, all right? We don't have to specify. So this is the same as this, if we prefer MATLAB, okay? But we don't have to. So this is pretty much very nice back compatibility. You know, if we have multi-dimensional tensor, we don't have to specify every dimension. So this is a nice thing about, you know, this tensor operation. And the other thing about, so for example, this is column 0, right? This is column 0, which is our first column. Let's change it to 1. So this is column 1, which is the second column. Okay, so we print it. So this is our second column, but you know, but it's print as a row vector, but we can track our second column is this. Which, yeah, I remember I put bigger on my mouse cursor. Why it becomes small again? So we can see this is column 1, which is our second column. However, we don't have to specify this. Is no matter how many dimensions we have, we can use this dot notation to represent, like we skip all the previous dimension. We're just interested in retrieve the last dimension. So, okay, so then we'll have this. Now we create this matrix, which has D sub n rows and n sub h columns. So let's do it. And now we want to implement this. Okay. So let's set b sub 1 0. So before we do that, so one way to debug is to check the dimension or the shape of every tensor. Okay. So if we have x has this shape, W1 has this shape, we can either do W1 transpose multiply with x multiply with W1 transpose, or simply x matrix multiplication with W1. Okay. So we do this, we get B2, and notice this little grad function here. Okay. Because earlier we put a requires grad true here. Is we'll talk about this next time in next coding lecture, that the gradient, the auto gradient function of PyTorch. So, and then we just do the clamp. So we're good. So everything negative becomes 0. Okay, so everything positive is unchanged. So this is for relative function. So the other thing I want to talk about is MM is different. So MM is different from this. Okay. So for example, so we have our x and W1, right? So here is x MM W1, but if we do this, I mean, right, the size of tensor match the size of tensor B in the single 10-dimension one. So this is different. This is different. Where I remember I had a cell, but where was it? Okay, here. So let's start something different. for example, what star gives us is, for example, we set this A equals maybe torch A range 8, okay? So now let's try to print 8 times A, okay? So it actually, we can see, it gives what we call an element-wise operation. So when we do A times A, okay, we get this. So this is similar to, so if some of us are familiar with MATLAB, this same behavior with dot multiply MATLAB, okay. But it's more flexible. In that we can actually multiply tensor with different dimensions as long as one tensor can be expanded as another. So I believe this is added in after maybe MATLAB 2021 as well, when MATLAB tried to catch up with the deep learning things. Okay, so, but now let's scroll down. Okay, so we have this error, but it's fine. So now what happens is, so here the data, okay, so the data shape is kind of different from, so this is like a single data. This X is like a single data. Like we have a single sample, so this X, all right? But in fact, what happens is we have like, so for example, so what PyTorch accepts is, if we read the manual, we'll find PyTorch's help is normally given in this way. So the shape of a tensor is normally how many samples in the batch and whatever this dimension is. Okay. So yeah, let's still do this. So if we have 8 samples in the batch, we do this, and we can, so we can do the same thing. So specify by this, and then we have something like this. So. And so this is a built-in function to do what we did just now. That is called NN linear. So it's a most simple one that gives us the same thing. So, for example, yes, let's first import this. Then this NN linear 10.5 is basically map something with last dimension 10 to a last dimension 5. Okay. So let's run this, and we can see it's doing the same thing. So with what explicitly implemented here, that is first matrix multiplication, then we do this clamp. Clamp is relevant. So layer 1 is we do the matrix multiplication, and then activation is we do the realm. Okay. Yeah, let's skip the autograph. Let's skip the autograph part. So now let's see a simple gradient descent algorithm. Okay. The simplest one is we use linear regression to fit data of a function. So this is a polynomial fitting using this polynomial, and then it converts to a linear regression problem. So, and x, this d sub h is like the sample point. So we use a cubic polynomial to approximate this f of x. So let's first import this math. Okay. This is not random input output data. It's just straight input output data. So for example, this so this is a linear space. Okay. So it's from minus pi to pi, and we have 2,000 points. And for example, so let's make new line. And this is delta x. So, and y is our, for example, we can print x shape, and we can print y shape. So x is basically, what happens is, x is basically our sample points. So let's try to see what linear space is. For example, if we have 0, 1, and 5, let's do 6. Okay. So what happens is, it just generates a sample points of equal spacing. So we can see that 0, 0.2, 0.4, 0.6, 0.8, and 1. Okay, so 6 points and 5 intervals. So now we just do, A, B, C, D to create the random initial weight, and we fix the learning rate to be this. Or it can be bigger, but let's be bigger. And then this is for t in range 2000. Okay, what happens is we basically run 2000 iteration of gradient descent. So this is our loss function. Okay, so this is our gradient. And then what happens is we just subtract each, so we want to minimize A, B, C, D, right? So we just subtract the gradient of each variable. So this means subtract. So for example, if we have A equals 5, okay, then if we do this, it's like setting A equals A minus 2 if we do this. So if we print it A again, we'll get 4. Alright, so this is minus equal, is just A equals. So in place version of A equals A minus 2. Because in some packages, this will create a copy of A in the memory, but this won't. Okay, so this allocates the same memory address. Don't create a copy in the memory. So this is basically a gradient descent algorithm, and let's run it. So next time we'll learn some more advanced manipulation. Oh, it's too big, okay, I guess. So now we have our cubic polynomial to approximate sign. So now let's plot it, and not that close, but it's okay. Okay. So yeah, but so I hope you guys like to run each cell by yourself, to see and to test different things, So, but I'll upload this to Canvas, okay, annotated one. So that's it for today. Okay.
Thank you.
You send me the tutor's lecture?
Yeah.
Like the first page.
Okay.
I just have it until or you can send me the whole thing.
Yeah, I'll send you the I just print PDF and access.
Yeah. I will work on 2 minutes and I will send you what I have. For
Yeah, I think I'm facing problem with the code. I'm not getting it.
yeah.
What's the
last one?
Yeah, the last one. And also the first one I'm trying to do it. I did one of the things told me. So this is the way.
Go for A.
Yeah, the front A. So this will be it's infinity, I think.
Yeah.
This cause infinity. When q is equal to
To 1.
no, the q is equal to 1, I think. Q is greater than 1, right? I think. What's going on?
And that was, the first one is linear, right? Or sublinear? Sublinear.
Yeah, the first one must be the sublinear and the second one must be the
I already
superlinear.
have the exam, but we will have to finish the CG's convergence. So, perhaps takes 2 classes. Let's see. So, now we'll do a review. Sometime around maybe
Oh, yeah.
October.
I just did it for B equal to 1, well, Q.
Yeah.
You change like you send it. But if it's, what you said, it's 1, if it's equal to 1, but in greater is just infinity.
Yeah, the professor said the x star is not going to be there. So if x star is not
Yeah,
there,
like
So we'll finish
then
on
it
CG
makes
This
a
is
lot
zero,
of a
that's
change.
0.
and then we'll have the midterm. Okay. So I will post the practice
And then this is
maybe next week. So yeah, we are moving on CG's convergence. It's the method is called the trial of substance, which I'll explain next time.
I only have notes with me. So in the one, so I go for this. This is the correct one.
It's my bad luck.
oh. Oh no.
So we
You have your homework done?
Almost, but I need to see the.
Let me ask you, why
I
this?
need
You want to
see the
compare?
thing.
Oh,
Yeah.
I don't understand this.
But wait, Adriana, I have your number. I will call you tonight or tomorrow. Yes.
This is tomorrow, right?
Yeah.
Tomorrow night, yeah.
Yes. So just for homework.
Yeah, we can.
Online, I will take compare.
Yeah, we can
Not
compare.
now.
Yeah,
I
yeah.
need to go.
I need to review this.
Yeah, that's it. So I will call you for
Okay.
for a meeting.
Okay.
Thanks. See, we have to.
What is this?
Just one.
it's
One, right? Yeah.
What is this?
simply
We divide k on each term. What limit is this? What limit is this?
0.
Yeah. What limit is this?
0.
Yes. Then what limit is this? So what limit is this?
0.
Okay. What limit is this when k goes to infinity?
0.
Then what limit is this?
1.
Yes.
For the
There
first
is
one.
many things.
I recommend you review calculus. Okay. So, what limit is this for fixed p? For fixed q? Q is something positive. What limit is this?
It's 1.
It's 1, yeah. 1 raised to the q power is still 1. Okay? Is that the same function you get when you have p?
When p is 1, yes, it's 1.
When p is 1, it's 1. Right. But p has to be 1 in order that the limit is 1. If p is not 1, you have an extra factor.
Extra factor, yes.
What is this extra factor?
P
P minus 1 times q. Okay.
minus 1.
Agree?
Yeah.
So this is k to the q power times k to the p minus 1 to the q's power. Okay. This limit is 1, right?
Yes.
When p is greater than 1, strictly, what's this? k raised to the p minus 1 to the times q power.
P is greater than 1. P is greater than 1. Infinity?
Yes, this is infinity. So it's 1 times infinity. You get infinity. It doesn't satisfy the superlinear convergence condition. The superlinear convergence convergence, we have to get a mu between 0 and infinity, which is a real number. This is infinity. So, yeah. So, like I said, in the homework, the first one is sublinear, second one is linear, the third one is superlinear. You just want to figure out what is p. Okay. So for the first two, you already figure out the p. I mean, I already told you the p. The p is 1. Okay. Good. Okay. The first two, you need to verify, but p is 1, and you want to find mu. For example, when p is 1, this is 1.
Yes.
Okay, so it's p equals 1, mu equals 1, so it's sublinear convergence. Yeah. The second one is linear convergence, because mu is a number strictly less than 1.
And the last one is?
The last one is superlinear, and you want to use some, so you want to figure out what is p.
Okay.
So the hint is p is 2.
But he said that if you already did that, you don't have to redo it. If you already
You want to try it?
Yeah,
Okay.
I'm studying, like, this is very new to me.
This is very new to you. You sure about that?
Not so really, but
No, so the idea is this is an application of calculus. So until we write it down, we didn't know it was calculus. You know what I'm saying?
yeah, I didn't study that much in our course.
Question?
Yeah, that's fine. We can meet tomorrow.
Thank you
Thanks.
for.
I think you're in my PDE class, are you?
Oh, yeah.
You are? Are you a grad student?
No.
Oh, you are?
Yeah.
You a grad student?
Yeah.
Oh,
My first
interesting.
and I graduated in May. Computer science.
Yeah.
Question?
No question.
Question? Okay.
And we will talk tomorrow or today. You can just message me if you don't have time today.
Yeah.
And then we can meet tomorrow.
Not tonight, because you have to submit tonight, so you could